we will get into the topic how search engines work. So, the scale which we have right now, let's consider the total online where we have multiple sites, like billions of sites, billions of pages, trillions of, no, not even billions, trillions of URLs, in the sense which are websites, which are constantly mutating content. Like, there are two different types of sites, which are static sites and dynamic sites. Even if there is a difference between the both sites, static sites is where the when maintenance update needs to be happen within the site, like suppose the data needs to be changed, then the system needs to be overrun by stopping the site for maintenance. But when it comes to a dynamic site, it can be updated real time. So we have two different types of sites, which is static and dynamic sites. The objective, given a single query, finding the absolute best pages. What it means is that, like for suppose when we type something in Google, Google is a search engine. Like Google has its own search engine. Google is the provider through which we go through trying finding content online. Like for suppose when we ask who is the Prime Minister of India, then it will try to find the most relevant content, right? So what it means by the absolute best pages is that a website can have multiple pages of multiple routings. So each and every page route can be considered as a web page. The constraints must be executed with high accuracy at planetary scale in milliseconds. The reason for it is because the we need to have a response input, and with this hard constraint, you need to know like how powerful the search engines are to be able to scroll through trillions of links and billions of pages to find the right content. The reality, without search engines, finding information would require scanning the entire internet sequentially, which is an impossible task. So search engines are a really important aspect, which is the core component, like when we do any searches. The three-stage information refinery. So we have three main stages which we have in regards to a search engine, where is the stage one, crawling, stage two, indexing, stage three, ranking. Crawling in the sense the search engine is going to discover, it is going to traverse the internet to find new and updated pages. For suppose the examples are Google bot or Ping bot. Google bot in the sense the bot which is used for crawling within Google search engine, and Bing bot is for Microsoft search engine, Microsoft Bing. Indexing. Indexing is the stage where we are going to organize the data. All the raw text which is discovered through crawling is processed, normalized, and cataloged into massive data structures for fast retrieval. So all the raw text will be organized into structured format so that it can be retrieved at a faster pace. Stage three is the ranking. It is the phase where the content according to the relevancy will be ranked. It is dependent on different types of algorithms which we use for the type of the ranking. There are different types of algorithms for ranking, and there are also different types of indexing ways like forward indexing, inverted indexing. Algorithms evaluate indexed candidates against a user's query to sort them by relevance and quality. So what it means is that all the indexed candidates which are found and organized by through the indexing step will be compared to the user query to sort them by relevance and quality. Discovering the web through automated crawling. So, The difference is just that automated and manual. Automated is where the crawling, where the discovery is automated. Like we are going to use bots for it. Seed URLs. Crawling begins with the foundation of highly popular domains and submitted sitemaps expanding recursively. So the main ones which automated crawling bot goes through would be the popular domains first, and it goes through based on these different types of structural syntaxes. Robots.txt. Robots.txt is a file which restricts automation. So based on the type of robots.txt which is there for the website, it is dependent whether the bot will work or not. This should be followed. The rules should be followed which are put by the robots.txt. Crawlers strictly respect robots.txt, a file where websites dictate which paths bots are allowed to traverse. So let's take an example of a e-commerce website. So a crawler bot can go through the home page, uh, product catalog, etc. But it cannot go through user information, user login page, payment page, etc. So in this way, this is one sort of an example. So in this way, there are restrictions based on the site organizers. The URL frontier, a massive queue containing billions of URLs waiting to be visited. The hidden costs of web traversal. There are mainly four different costs, which are crawl budgets, which is dependent on the computational resources. Like search engines actively limit requests per site to avoid overloading external servers. So there are going to be restrictions on how many requests which can be sent per site based on the duration. Prioritization is given to authoritative and frequently updated news sites over inactive ones. So what it means is that the ones which are given priority are the ones which are updated the more. Duplicate detection. The internet is filled with mirrored pages, like having the same content over multiple pages, and which can be copied content or the same or different people writing about the same topic which are almost similar. So crawlers are going to use hashing, cryptographic hashing, and canonicalization to filter out redundancy because redundant outputs is not what we require, right? So the redundant ones will be removed. This is called as duplicate detection. Next is JavaScript rendering. JavaScript rendering takes a lot of cost for web traversing because JavaScript causes a lot of different types of heavy processing workloads. So, which JavaScript previously wasn't there. There was only HTML and CSS, HTML which is for the structure and CSS for the styling. But after JavaScript has been introduced, it caused a lot of heavy workloads for the crawlers because it requires the crawlers to use headless browsers like Chromium to execute the JS and waiting for APIs. It increases the computational cost by a lot. Distributed architecture. Google scale crawling requires thousands of distributed crawlers clusters operating simultaneously because we do require multiple clusters, right, so that it can be parallelly processed because there's a lot of content online and there are a lot of requests sent by millions and billions of users. Flipping the data unlocks instant retrieval. So there we have the inverted index, which has been introduced, which is one of the best indexes. It became the foundational architecture of all search engines. So inverted architecture is where let us consider there are three documents, and each document is going to contain the data, right? Like for suppose engine, search, and fast in one document, data, engine, and web in one document, fast web code in another document. So each and every word within the documents will be mapped to the documents in which these words are contained. So for suppose engine, which is contained in document one and document two, so it will be indexed to document one and document two. So yeah, it will have the same for the other data which is available within the documents. The mechanism. Instead of mapping documents to words, we are going to map the words to the documents. This is the difference when it comes to a forward index to a inverted index. The result, finding every page containing the word in the engine becomes an instant lookup rather than an endless scan. So what it actually means is that, like for suppose, rather than scanning each and every document to find the words, it's easier if each and every word within the document is mapped to the document. I mean, word within the documents is mapped to the documents, right? So this index will become easier, like an instant lookup to the document where these words are exist. So this will be very easy. So because when it comes to the standard layout, it requires scanning each and every document for a match. But when it comes to the inverted index, we just need to look where the term exists. So it's a direct term to document lookup. The complexity in the first is often where each and every document needs to be scanned. And when it comes to the complexity for the inverted index is just O of 1 or O of m, O of log m, O of log m where m being the number of documents, like the word existing in the number of documents. Those number of documents would be then log m, O of log m. Preparing raw text for the catalog. So let us consider the raw text input, the running foxes. So it will be tokenized first. Tokenized is where the sentences are broken down. The textual data is broken down into tokens, which are fundamental units to be considered when it comes to natural language processing. So it will be uh, broken down into searchable units. Next is the normalization, where normalization stop words, where the words like the, and, a, for, etc. will be removed. And the normalization is where we are going to convert with the lowercase, remove the punctuation, and dropping down lower value words. Lower value words are the words like for, of, the, and, a, etc. Stemming and lemmatization. So stemming and lemmatization is where we are going to reduce the words to the root forms. So this is going to improve the match rates. Metadata extraction, pulling out structured data, anchored text, and HTML headings for later ranking signals. So at the end, we are going to have the final index where the run and fox are the main words which are required to be indexed. The millisecond journey of a user. Let's consider an example where we are going to search for the restaurants near me. So the phase one is understanding the query. The system analyzes spellings, synonyms, language, and user consent. Next, we go for the indexing, where we are going to go for the most used index, inverted index, which became the fundamental indexing algorithm for all the search engines. The system queries the index, inverted index, to instantly pull thousands or millions of possible matching documents. Next, we have the ranking engine, where the unorganized candidates are sorted by relevance and quality before being displayed. So all in all, it takes around 200 milliseconds for the process. Treating links as votes of importance. The breakthrough. This is invented by Larry Page and Sergey Brin. Page rank mode search beyond easily manipulated keyword counting. The core idea, every link acts as a vote. Both the quality and quantity of incoming links determine a page's authority. The random surfer model. Imagine a person clicking links forever. The pages they land on most frequently hold the highest page rank. So page rank is in the sense by various metrics like the number click-through rate, etc. The high authority node, heavy authority transfer, minor authority transfer. So this is the mathematical representation which is given for the page rank. Authority flows through the graph, decaying slightly at each step. So PR of A equal to 1 minus T plus T plus into sum of PR of T by C of T. This is like the mathematical representation which is for the page rank algorithm, where PR is the page rank and D is the distance. Hundreds of signals determine final relevance. Beyond links, modern ranking uses hundreds of machine learning signals to sort candidate results. So after the introduction of machine learning, like it has started to use machine learning signals to sort candidates results based on various different types of features. The EEAT framework, assessed continuously by human quality raters to ensure, which represents experience, expertise, authoritativeness, trustworthiness. Freshness, critical for news and trending topics. A rapidly changing query requires recent content. Engagement uses click-through rates and read times to measure actual user satisfaction. If user satisfaction immediately bounce, the rank drops. So performance penalizes slow loading pages and non-mobility friendly layouts, prioritizing user experience. So what it actually means is that all these metrics become the features through which we are going to analyze the relevance, engagement, authority, speed, and freshness. These are the metrics through which determines how the pages will be ranked, how the links will be ranked. Distributing the index across millions of servers. The latency mandate. Typical target latency is under 200 milliseconds per watt. User query goes to a load balancer, which is going to store the results of popular queries to bypass competition entirely, so that it is not required to go for the process again. We are going to have the load balancer, which is going to save cache the results which are the most popular based on the popular queries. Parallel routing. We are going to have a distributed system, which we are going to have, where we're going to have multiple servers, where the massive inverted index is physically split across thousands of machines. This is called as distributed computing, so that there is no overhead for a single machine. We are going to have parallel processing per se when we have the distributed computing. A single query is routed to all shards simultaneously, processed in parallel, and aggregated, enabling infinite horizontal scale. So we have two different types of scalings. One is the horizontal scale, where we are going to have multiple units which can be processed parallelly, and we have the vertical scaling, where a single server's computation will be enhanced, will be an advanced multiple times, but the overhead will be very high when it comes to a single system. So depending on our problem, we are going to consider whether we are going to choose a distributed system or a vertical scaling. Mapping meaning in the vertical vector space. The semantic shift, moving past exact keyword matches to understanding deep context and relationships via transformers. So before we used to use exact keyword matches, but after artificial intelligence has advanced, we are using semantic searching, where we are going to understand the context and the relationship via transformers models. Embeddings. AI models convert text into dense array of numbers, which are called as vectors. Vector similarity. Semantically similar content is physically located closer together to the vector space. The infrastructure, powered by specialized vector databases. Example, Pinecone, VWeight, designed to calculate nearest neighbor distances instantly. So let us consider this vector space, where we are going to calculate the nearest neighbor distance calculation. So we have the three different coordinates, where one we have the apple fruit, apple company, and king and queen, which are units. So within the vector space, like all the texture data will be represented in the form of a vector space, numerical representation of arrays in the form of vectors. Augmenting generative AI with live retrieval. The RAG architecture. RAG means retrieval augment generation, where which becomes the engine for the modern AI assistants and enterprise search. Like it is going to have semantic databases, which are vector databases connected to the RAG model, and all the semantic searches happens. The code. LLMs alone hallucinate and lack real-time data. Search engines alone provide links, not synthesized answers. So it is a hybrid approach of having both LLMs and the search engines, where we are going to have the RAG architecture. The synergy. Search engines retrieve the factual content, LLMs use the context to generate a precise human readable response. So that's how we are going to have when it comes to an LLM. Like LLM is connected to a search engine where the retrieval happens through retrieval augment generation. First point, which is the user asking a question. Second, where system queries vector database. Third, where top results are retrieved through the ranking algorithm. Fourth, where results plus original prompt are fed into an LLM. Fifth, where LLM generates a grounded, accurate answer. So this is what's happening in the current LLMs like ChatGPT or DeepSeek or Grok. Whenever you turn on the search feature, the evolution from keyword matching to context. Previously and the current one. Previous one, which is called as a legacy search, and the current one, which is a modern semantic search. The core mechanism. For the legacy, it's the keyword counting, and for the modern, it's the vector embeddings and transformers. Data structure. Standard inverted index is used in the legacy keyword search, and modern semantic search uses vector databases plus inverted index. So inverted index is still being used because the algorithm which we have within the inverted index is itself is a really fast algorithm. Matching logic. Exact string matches for legacy and intent and meaning based matches for modern semantic search. Vulnerability. Easily manipulated by keyword stuffing. But when it comes to modern semantic search, highly resilient via AI trust scoring. Primary output 10 blue links, like based on the number of links which are set by the search engine. But when it comes to modern semantic search, synthesized answers and personalized results. Defending the index against manipulation. The adversarial vessel. Search ranking directly drives revenue, creating massive financial incentives for manipulation. Black hat SEO, which is called a search engine optimization. Spam tactics. Bad actors use fake link networks, scraped content, and hidden text to artificially inflate page rank and relevance. The mitigation. Search engines consistently deploy graph analysis and anomaly detection to identify and penalize manipulative networks, which are using these type of spam tactics of advertiser web, maintaining the integrity of the results. The ultimate search engine mental model. First is a crawler, the second is the inverted index, third is the ranking engine, fourth is a page rank, fifth is a semantic search instead of the legacy-based search. So previously we have already discussed regarding what a crawler is, what an index search inverted index is, what is a ranking algorithm, what is a page rank, and what is semantic index search.